In this work, we propose Keypoints into the Future, a novel approach to model-based reinforcement learning that leverages self-supervised, dense visual correspondence. Previous work introduced self-supervised dense correspondence to learn visual object representations for robotic manipulation. Subsequent work showed how these dense correspondence models could be leveraged as input to visuomotor policies to perform efficient imitation learning. Our prior imitation learning work suffers from several drawbacks. In particular, it requires expert demonstrations, doesn't leverage off-policy data, and can't be used to achieve diverse goals at test time. Keypoints into the Future combines the benefits of our prior works, leveraging dense descriptor-based keypoints, with model-based approaches that can learn from off-policy data and achieve diverse goals at test time. Many standard approaches in robotics pose the problem in terms of states, actions, system dynamics, and the reward that defines the task. In practical robot manipulation scenarios, however, we typically don't have access to states, dynamics models, or a state-based reward. What we do have access to is the observations, typically in the form of images. Our approach is to learn a function g that maps the observations to a latent state z, in which you can learn the dynamics and specify the task. In order to learn a dynamics model, we must determine the latent state z and how to estimate it from the observations. Prior work has used pose, full image dynamics, or a low-dimensional latent state from an autoencoder as the state z. We propose to use 3D object keypoints. Our dynamics model then learns to predict the evolution of these keypoints given a sequence of actions. We use our self-supervised dense correspondence model to track a sparse set of 3D keypoints on the object. Our visual model also predicts confidence scores for each detected keypoint. In this case, the green keypoint displays a high confidence since there exists a valid correspondence, while the red keypoint is occluded in the target image and thus has a low confidence. A key question is how to extract sparse keypoints from the dense correspondence model. We propose two approaches. The first selects keypoints based on confidence scores and spatial separation, while the second uses a convex combination of keypoints with a learned weighting. To learn a dynamics model, we collect unsupervised interaction data. Our approach allows for predicting multiple time steps into the future by repeatedly applying the dynamics model. The model is then trained to minimize the multi-step prediction error. Our approach was trained using just 10 minutes of real-world interaction data. In contrast to prior work, we do not require expert demonstrations and can take advantage of off-policy data. Here we show the performance of the learned dynamics model. Ground truth keypoint tracks are shown in green, while the multi-step predictions from our learned model are shown in blue. At test time, we use the learned dynamics model in an MPC framework to perform closed-loop feedback control. Given a goal state or a trajectory, we can define a reward based on a final state or trajectory tracking cost. Using the learned dynamics model, we can solve a trajectory optimization problem to compute a sequence of actions that maximize the reward. A single demonstration can be used to provide a trajectory of 3D keypoints for the MPC problem. We emphasize that our latent keypoints are in 3D and aren't restricted to pixel space. Here we demonstrate our full system in action. On the left is the current image, on the right is an alpha blend of the current and goal image. The current state is in blue, and the goal state is shown in green. This is the demonstration trajectory, and the predicted state from the MPC output is shown in purple. Control actions are computed online by the MPC at 5 Hz. As can be seen, the controller is performing continuous feedback to track the trajectory and drive the object to the goal state. Since our system is performing closed-loop visual feedback, it is robust to external disturbances and can still stabilize the object to the goal. Another benefit of our approach is that once we have trained a dynamics model, it can be used to achieve diverse goals at test time. Here we show examples of tracking 4 different trajectories, each obtained from just a single demonstration. Our perceptual representation is also robust to visual clutter and distractor objects. To demonstrate the reliability of our system, we showed 10 consecutive rollouts starting from different initial conditions. In general, our system is able to stabilize trajectories from a wide range of initial conditions. We proposed a novel formulation of model-based RL using self-supervised dense correspondence to track 3D object keypoints. We use this representation to perform real-time feedback control for a non-prehensile manipulation task on real robot hardware. In our paper, we also perform quantitative simulation experiments showing improved performance over a variety of baselines. Please see the paper and stop by during the interactive session for more details.